Great. So today we're going to talk about statements and proofs. So this is something that you have seen a lot in mathematics, and what we're trying to do. And if you have read the TMUA notes, I think you would appreciate like how universal it is, right? You have definitely seen if statements before. You've definitely been asked to prove if statements before. And what this lecture is trying to do is that we're trying to make those concepts a little bit more rigorous and less hand-wavy. And I think it's definitely very crucial to build a very solid foundation on the basics of propositional calculus, because these are the things that you're going to be doing all the time when you're doing mathematics. And it's just a good idea to get a grip on them, get a firm grip on them. So, well, the first thing is that this is going to be a lecture, right? And a lecture is really a concept at the university, and you're not going to have lectures in high school, and you're only going to have classes in high school. And so the main difference between high school and university is that, in high school, all of your learning is in like the 6 hours classes that you have every single day. But at the university, you only really get like 1 to 2 hours of lectures per day. Does that mean that you spend all the rest of the time playing? No. The point of a university education is that you're expected to learn on your own outside of the classroom. You're expected to read the notes yourself. You're supposed to read books yourself. You're supposed to spend a lot more time in the homework that you're doing. You're supposed to really constantly refer to your lecture notes and the books when you are doing the homework. And so it's really a very self-focused learning experience. And I hope that through this course, I'm also going to be able to give you some of that experience. So this lecture is going to be very short, but the point of it is that I'm just going to give you a brief overview of the things that you're supposed to learn, and so that you would know what you're struggling with, what you'll find interesting, what you understand fully, so that when this lecture ends, you're going to be able to spend time on your own, getting a further grip on the material and succeeding in doing the problem sheet. So let's begin. So in mathematics, you have dealt with sentences all the time. Even in the most simple mathematics that you will see, they're usually composed of rather complicated sentences. So for example, in the sentence, if x is odd and y is odd, then x times y is odd. Now that is a very simple thing that even primary students would know. But in this complicated sentence, it's actually quite complicated, because if you try to decompose it into its basic elements, there's actually 3 sentences, right? X is odd, y is odd, and x times y is odd. And when we try to make this complicated sentence, we make use of connectives. So we would use this connective if then, and we would use the connective and. So this seems like kind of an English lesson, but it's interesting, right? Because all these sentences and connectives actually have a very rich mathematical meaning to it. It's not just about English, if you think a little bit more about it. So here's another example. We also say, if ABC is a triangle, then the sum of the angles is 180 degrees. And in here, there's actually 2 sentences, right? We have the first sentence, which is that ABC is a triangle, and the sum of the angles is at 180 degrees, means that the angle of ABC plus angle of BCA plus angle of CAB is 180 degrees. And we use the connective, if then, to connect these 2 sentences together in order to form this more complicated and very rich in meaning. So the basic idea is that in mathematics, we are always combining basic sentences into forming complicated sentences that is very non-trivial. So how do we formalize this concept? So for now, we are going to think about sentences, and we would only consider truth functional combinations. So what we mean by that is that whenever we are making new sentences, like this sentence, the truth or falsity of this new sentence is only going to be dependent on whether this sentence is true and whether this sentence is true. So we are not going to have any hidden variables. We're not going to have any hidden sentences. We're only going to be considering the truth or falsity of the component sentences. And we are also going to use 5 propositional connectives. So in order here, we have the negation, the and, the or, the implication symbol, and the if and only if symbol. So these 5 propositional connectives are not an exhaustive list, nor are they like the only connectives that you ever need, but these are simply the most common connectives that you would see in mathematics literature. So whenever we say of sentences, here are some even more examples of sentences, right? Paris is the capital of France. Rome is the capital of France. We are going to consider sentences that are either true or false. So they cannot not be true or can. So what I mean by that is that sentences have to be either true or have to be false. They cannot be uncertain, and it's always either true or false. So that's actually quite an important bit. That's called the law of the excluded middle. And by considering sentences that are either true or false, we're going to simplify our analysis a lot better. So we are also going to use alphabet to stand in for sentences. So we can say, for example, we would say that A, the letter A, would stand in for this sentence, or we can say that the letter B stand in for this sentence. Again, it makes talking about the propositional calculus a lot easier to understand. So let's start by talking about these propositional connectives and what they actually mean. So the first propositional connective is the easiest one, which is the negation. And we would use a truth table to represent this. So as we have said before, a sentence can be either true or false. And so whenever we are trying to define a propositional calculus, we only need to consider all the possible cases, right? And in the case of negation, there's only one letter, and so we only have to consider 2 cases, when A is true and when A is false. And as long as we can say what the negation of A is in these 2 cases, we have a very well-defined operation on A. So in here, the negation of A is defined to be false when A is true, and is defined to be true when A is false. So this is a very simple example. For example, the negation of x is equal to 1 is x is not equal to 1. So now we're going to go to a more complicated propositional connective that involves 2 symbols. We're going to be covering the conjunction. So if A and B are sentences, A and B denotes A and B. So we pronounce this symbol as and. And we also say that A and B is true when and only when both A and B are true. And that it's going to be false otherwise. And so now we have this more complicated truth table. And the reason there's 4 rows is that we have to account for all possible assignments of true values to A and B. Because A and B can be true or false, there's only going to be 4 cases. And to be able to define the conjunction symbol well, we would need to account for all these 4 cases. And so we would say that A and B is true when A and B are both true, and then A and B is going to be false in all other cases. So these are all very simple TMUA note stuff. I believe you have looked into the notes. But the main idea is that in a truth table, we always need to account for all possible assignments. And so when there's 2 statement letters, we're going to have 4 rows. When we have 3 statement letters, we're going to have 8 rows. The core idea is that we need to make sure that whenever we use these propositional connectives, they are well defined. We have accounted for all possible cases. So now we will go to the disjunction. This is typo. This should be or. So when this symbol means or. So when we say A or B, we mean A, this weird symbol B. And a way of understanding this is that what we're actually saying is that at least one of A and B is true. So this is also what you would call an inclusive OR. So an inclusive OR means that both things can be true at the same time, right? in this sentence, it is possible that A and B are both true at the same time. This is different from the exclusive or. So for example, if I say to you, okay, you can either have beef or lamb as lunch. When I say that sentence, what I mean is that you can either have lamb or beef, and you cannot have both at the same time. So in English, we usually use the exclusive or more often, but in mathematics, we usually use the inclusive or. Another way of looking into it is that A or B is false when and only when both A and B are false. This is, I think, a neat way of looking into it, because this kind of looks similar to this. And so you can kind of link things up. You can kind of link conjunction and disjunction together. They are kind of the same sides to a coin. So now we have the conditional. So this is very, again, you've definitely seen this before. If A and B are sentences, A implies B. So we call this the implication symbol. We say this as A implies B, or we say that as if A then B. And it means if A then B. And in English, what we actually mean is that if A is true, then B is true. If A is false, then B can be true or false. And so in the truth table, it's quite interesting, right? When A is false, the A and B, if A then B, as a sentence form, is always going to be true. So this might be a little bit confusing, and at least in the English sense, you might not really understand why if A then true is true when A is false. But one way of kind of understanding this is that, well, first of all, you can think of it as, okay, we are just defining if A then B, right? We don't actually need to connect this to English, right? You can think of it as, okay, we're just defining if A then B with this truth table. You can, and when you think about it that way, then you can kind of ignore the English side of things. And so whenever you're doing mathematics with the statement if A then B, then you just stick to this truth table, and only use this truth table when you're thinking about things, and it should hopefully make things easier. Another way of looking into it is that is with some examples. So under our definitions, the following sentences are true. So if 1 + 1 = 2, then University of Oxford is in England. This statement is true, and this statement is true. And so if you look back into the truth table, A is true, B is true, and so if A then B is true. And in terms of our English understanding, this makes sense, right? Of course, this statement is true, because we're saying that if something is true, then something else is true. In a sense, this sentence really doesn't have the causation. So in some sense, when we are saying if something then something, usually we have like we imply there's a causation, right? So for example, if we say if you don't eat lunch, then you would feel hungry. And when we say that, we imply that this is a cause of this. But in this sentence, this is not true. 1 + 1 = 2 is not a cause for University of Oxford in England. But again, in mathematics, this sentence is true. Now, this sentence is also true. If 1 + 1 is equal to 3, then University of Oxford is in England. And this is because, again, this statement is obviously false, but this statement is true. And again, it is in this truth table, A is false, B is true. And so A implies B is still a true statement. I mean, here, this is actually a more interesting example. If 1 + 1 = 3, then pigs can fly. 1 + 1 is obviously not equal to 3, and pigs obviously can't fly. But this is still a true statement in terms of our definition. And a way of thinking about this is that we usually call these sentences as vacuously true. So by vacuously true, it means that the premise is always false. So because 1 + 1 = 3 is always false, no matter what you say after the then, the if statement is still going to be true. So if 1 + 1 = 3, then the earth is square. If 1 + 1 = 3, then University of Oxford is in France. These are still true statements in mathematics. And so this is kind of an interesting distinguishment between English and mathematics. And so you can think about this more on your own. So now we have the if and only if. So if A and B are sentences, A if and only if, B means A if and only if B. So we use this symbol to mean if and only if. And A if and only if B is true when and only when A and B have the same truth value. So in the truth table, you can see that A if and only if B is true when and only A and B are both true, or A and B are both false. If A is true then B and B is false, then A if and only if B is false, etc. So you can also think of this as saying that two things are equivalent. So for example, saying that I eat breakfast at 10 a.m. is equivalent to the statement that at 10 a.m. I eat breakfast. So if and only if basically means that they mean the same thing. So now we've went through all the propositional connectives, right? We have went through the negation, the or, the and, the implication, and if and only if. And in mathematics terms, they are called propositional connectives. And as you have seen before, any statement that is built up by these connectives has a truth value that depends on the truth value of the constituent sentences. And you can definitely see this in the truth tables that we've said before, right? You can see that A if and only if B, the truth value of A if and only if B is dependent solely on A and B. In other words, if you know the truth values of A and the truth values of B, then you would know the truth values of A if and only if B. And this all comes back to the earlier concept of true functional combinations. So whenever we are using these propositional connectives, we are forming true functional combinations. And this is a very important concept. And yeah, and now we're going to define a new thing. We're going to define statement forms. Statement forms are expressions built up from the statement letters by an appropriate application of propositional connectives. So whenever we use propositional connectives to connect these statement letters, we are going to call them statement forms. And again, as a reminder, statement letters must have one and only one true value, true or false. So, okay, so there are two rules with, there are kind of three rules with statement forms. First of all statement letters are statement forms. And if there's two statement forms, then we can make new statement forms by all the propositional connectives that we used before. And we also say that all statement forms must be generated by statement letters and propositional connectives. So in some sense, as long as you have some statement letters and as long as you have some propositional connectives, no matter how you combine them with parentheses and whatever, they're going to be statement forms. So yeah, this is basically propositional calculus. So propositional calculus only cares about propositional connectives and statement letters. And in that sense, it's actually a very elementary system of mathematics. It's a very simple concept, and we're going to talk about that a little bit later as well. So now we are going to define a new thing, which is called the truth function of n arguments. This is a function of n arguments, and the arguments and values of which are the truth values, true and f. And we have seen that any statement form containing n distinct statement letters determine the true function of n arguments. What this means is basically that, for example, in here, you can actually treat this as kind of a function, right? This is a function of two variables, a and b, and it spits out a truth value depending on the truth value of a and b. And so in some sense, this is kind of like a true function. Or when you think about negation, this is a true function of one variable, right? We take in the true value of one variable and then we spit out a new true value. And so you can think of this as a function. If you have read about functions before, you can kind of connect this with functions, which is a kind of a good way of thinking about things in terms of intuition. So let's move on. And now we're going to define a new thing called a tautology. A tautology is a statement form that is always true regardless of the truth values of its statement letters. So in some sense, this is what we mean when we say a statement is true. When we say a statement is true, we mean that it is true all the time. No matter what happens to the statement letters, the statement form is still going to be true. and that is what we call a tautology. So for example, show that A and B implies A is a tautology. If you think about this in English, it's very obvious why that's true, right? If A and B are both true, then of course A is going to be true. And this is what we call a tautology. This is a statement form that is always true regardless of if A or B is true. And you can prove something is a tautology by using a truth table. So in here we have a very basic truth table. The first two columns are standard, and then we write about, okay, so what is the truth table of A and B? We write that out. What is the truth table of A? We write that out. And then in here, we use the definition of the implication symbol to determine the fifth column. So in here, we see that A and B is true, A is true. So is A and B implies A true? Well, we go back to the implication truth table. We see that if A is true, if B is true, then A implies B is true. So we write down true here. As another sample, in here, we know that if A and B is false, then this is always going to be true by vacuous truth. And so this is true, this is true, this is true. And so we see that A and B implies A is always true, regardless of whether A and B are true or false. And so this is a tautology. As another sample, you can read about this at home. We can easily show that A or B implies A and B is a tautology using a similar method, and checking and referring to the implication truth table, we can deduce this very easily as well. So now we are going to also define two things. We're going to define we're going to let B and C be statement forms, and we are going to say that B logically implies C if and only if every truth assignment to the statement letters of B that makes B true also makes C true. And there's also the definition of B and C logically equivalent, and that basically means that if B and C receive the same truth value under every assignment of truth values to the statement letters. And we also have a proposition that says that B logically implies C if and only if B implies C is a tautology. So this is basically a way of understanding, or in some sense explaining, why tautologies are important. If you're kind of confused about that, you can kind of read this after the lecture, but this is actually just a way of kind of because it's kind of annoying to say that B implies C is a tautology, right? It's much easier to understand if we say that B logically implies C. And when we say B logically implies C, we actually mean this. And so it's kind of useful to, if you want to, you can try to think about this back home. And I think it's not that difficult to kind of understand why logical implication and tautology has a connection between them. And here's, I think it's a good time to introduce the book, Introduction to Mathematical Logic. It is a very good book. In fact, the lecture slides are honestly very much inspired by the book, and so I would recommend you to really read the book after the lecture. I think it covers kind of more advanced material at the same time, but I think it's a really good experience to try to learn reading on your own and trying to learn absorbing new information on your own. You will be able to find the proofs of these propositions in the book, and so I would really recommend you to really read the book yourself and try to see if you can understand the book yourself. So tautologies are obviously very important in logic, right? They are statements that's always true, and we use tautologies a lot when we're doing mathematics. So here's a few common tautologies. So the first tautology is P and not P. This is the law of the excluded meter. This means that every statement is either true or false. There's also the modus ponens. This is where if you have the statement if P then Q and P, then this implies Q. This is something that you use in mathematics all the time. For example, if you have a triangle ABC, then we can say that, okay, because we have a triangle, that's P, and because we know the law of angle sum of triangles, that's P implies Q, we know that the sum of the angles of the triangle is going to be 180 degrees, and that's Q. So this appears in mathematics all the time. You have definitely used this before. We also have De Morgan's rule. If you have read TMU notes, you have to know this. It also appears in, it's hard to say where it will appear in, but again, it's a very common mathematical tautology. You can read more about these on your own time. So because conditional statements appear in mathematics so often, so many theorems are in this form if A then B. In fact, in my university studies, almost every theorem that I've read is in the form if A then B. And so, since they appear everywhere, we do a lot of things to conditional statements. So the first thing that we can do to a conditional statement is to have the converse. So if we have P, if P then Q, then the converse is defined to be Q, if Q then P. So we say this a lot in mathematics as well. For example, I suppose you must have heard this before. And we also have the contrapositive. So this is kind of a little bit more interesting. Instead of saying if P then Q, we say if not Q, then not P. This seems kind of counterintuitive, right? Why would we ever want to do this? But turns out contrapositives is actually extremely useful in mathematics. So here's a proposition. Turns out if P then Q is logically equivalent to its contrapositive. If not Q, then not P. So the proof of this is quite simple, right? You really just explode the truth tables, and you would wait a second. I'm drinking some water. So you could try reading this truth table on your own. So again, it really is just reading of the truth tables, right? We have not P to be this, we have not Q to be this, and then when we try to read off this, how do we deduce this fifth column? Again, we use the truth table of the implication symbol, because this is false. Because not Q is false, this has to be true by vacuous truth, and then this is false because this is false because not Q is true but not P is false, and then this is true because both things are true. So yeah, this is basically a proof of why contrapositives is logically equivalent to the if statement. And finally, we're going to introduce more vocabulary of if statements. So mathematicians like to use a lot of vocabularies to mean the same thing. And whenever we say if P then Q, it means the same as Q if P. It also means the same as P only if Q. It also means P is sufficient for Q, and it also means Q is necessary for P. You can try to think about this on your own time. So, for example, P only if Q. So why is this? Why does this mean the same thing as this? Well, you can think of it as P only if Q, right? So if Q, how can you think about this? P only if Q. What this is basically saying is that there's no way that P is true if Q is false, right? So P is only true if Q is true, because if P is true, then Q is true. So again, it's kind of hard to kind of explain this with words. So I would recommend you to kind of think about this and how it connects with English. Why does sufficiency mean this, and why is necessary mean the opposite of that? I think it's good to kind of try to incorporate these vocabularies into your own brain. So yeah, you can try to figure this out on your own. So the logic that we have all covered before is called propositional logic, and I hope that you can see how truly limited it is, because again, when we think about statement forms and statement letters, we can only deal with things that involve letters, and those letters have to be either true or false, and we can only deal with propositional connectives, and there's only 5 of them. So as you can see, it is not capable of dealing with non-logical objects. Like, there's no concept of an integer, right? An integer is a number. It is not a statement form, obviously, and like we don't even know what addition is, we don't know what multiplication is, we don't know what the equivalent sign is, and so propositional logic is woefully limited, and so we only have statement letters and statement forms, right? So for example, the following aren't statement forms. A, the sentence A is false. Like again, we aren't, what is English? Like we don't understand English, we only understand statement letters and statement symbols and propositional connectives. It's the same for 1 + 1 = 2. However, propositional calculus still appears everywhere, and in some sense, it is kind of the foundation of mathematical logic. So if you want to deal with integers, and if you want to deal with what these are basically called quantifiers, you're going to have to use first order logic. And you're going to need first order logic in order to rigorously define integers, addition, multiplication. For example, you might have heard of piano arithmetic, or you might have heard of like set theory and like TFC. And in order to do those stuff, you're going to need a lot more advanced logic. But my main point is that propositional logic is still very important on its own, and even if you only know propositional calculus, you're still going to be able to use it to make sense of the mathematics that you deal with every day. And so now we're going to take a leap of faith, right? We're no longer going to be concerned with the rigor and the formalities of things, and we're going to see how we can take concepts from propositional logic and kind of trying to apply it to the world of mathematics that we know. So let's try and do that. So again, as I said before, if A then B is one of the most common statements that you would see in mathematics. And so let's start off with an extraordinarily simple proposition. If x is even, then x squared is divisible by 4. This is a primary student would know this. However, the challenge here is that we are going to now try to be proving statement forms. So whenever we are doing propositional calculus, we are proving if stuff are tautologies, right? But tautologies are kind of, in some sense, they only help us prove stuff. If we want to prove stuff in real life, we would need axioms and we would need theorems and axioms and theorems. And so tautologies alone cannot help us prove meaningful things in real life. We also need axioms, and we also need basic facts. And so, but in what we'll discuss further on in this lecture, we're going to try to use tautologies to help us prove stuff, to help us understand why we prove things the way we do. And so, well, first of all, let's try to unpack this statement, right? The above is an if A then B statement where A is x is even, and x squared, and B is x squared is divisible by 4. And when we are asked to prove a statement like this, we usually do it by three ways. We usually prove it directly. Well, what does that mean? We're going to explain it later. We also can consider the direct proof of the contrapositive. That's kind of new. I don't know if you have seen this before, but it's a really exciting way of proving things. And we will also be using the proof by contradiction. And again, these two, I think, even if you think that you know them, you might not actually really understand the fundamentals of it. And in some sense, you really don't use them that often. Most of the time, you just do a direct proof. For example, in DSC geometry, all the proofs that you do are direct proofs, right? And we will see that soon. So first of all, we would cover the direct proof. So the fundamental idea of a direct proof is that we want to form a chain of implications. We want to show that A implies a slightly different thing, and then we want to show that slightly different thing implies another different thing, and then it's through all these steps that we end up with the thing that we try to prove. And in all of these symbols, the reason why we can make these implication symbols is justified by our knowledge of integers, by some very basic facts, by some very basic geometry facts that you're able to use, or by axioms. This is clearly quite a hand-wavy way of explaining things, but again, if you want to understand how we deal with axioms and how we deal with basic facts, then again, read mathematical logic on your own. So for example, if we were trying to prove if x is even, then x squared is divisible by 4, we would say that, okay, well, x is even, right? So then, by some basic facts of integers, right? Everyone knows this. We would know that x is equal to 2n, where n is an integer. And so, okay, well, we know that if two things are equal, then we can square them and they will still be equal. Again, the reason that this works is because of some mysterious knowledge that we are expected to know, and so we can deduce x squared is equal to 4n squared. And so, well, okay, so that means that x squared has 4 as a factor, and so x squared is divisible by 4. So this is like, for example, this is basically how you do a lot of the geometry in DSE. For example, if you want to prove like, I don't know, if you want to prove like, there's a triangle and you want to prove that the sum of the angles are 180 degrees, you would justify the implication symbol. So for example, here, let's say ABC is a triangle, suppose that this means the sum of the angles is 180 degrees. In this implication symbol, you would kind of justify it by writing down, okay, sum of the angles is 180 degrees. And in DSE, this is allowed because you're only allowed to quote a certain number of theorems. And so, yeah. So I hope that you kind of have a feel for this. So in some sense, a direct proof is that we separate a short implication statement into a long chain of implication statements that is justified by some simple facts or by some simple theorems that you're supposed to be know. As an aside, you can also try to show that this statement form actually logically implies this statement form. Again, this is kind of a more formal way of understanding why direct proofs work. This is not very difficult, and you can try to do it on your own time. So now we're going to think about direct proofs of the contrapositive. So we call that the contrapositive is logically equivalent to itself, right? And so instead of proving an implication statement directly, we can actually try to directly prove the contrapositive instead. So if we directly prove the contrapositive, we immediately prove the original statement, right? And this is because of the logical equivalence. So instead of proving that if x is even, then x squared is divisible by 4, we would try to prove if x squared is not divisible by 4, then x is odd. Again, you can do a direct proof very easily. For example, x squared is not divisible by 4. That means that x squared is not divisible by 2, and that means x squared is odd, and so x is odd because of some basic knowledge of integers. And this is a perfectly valid proof of the original statement that we already have. So I don't know if you have tried this before. I think that this is a very valuable tool. A lot of things, even though in this case a direct proof of the contrapositive seems kind of how could I say it, more complicated. It doesn't seem that intuitive. But in a lot of cases, proving something by its contrapositive is actually easier. And so whenever you're asked to prove a complicated statement, you can try to think about the contrapositive and see if that is easier to prove instead. Now we also have the proof by contradiction. And I think the proof by contradiction is something that's very often misunderstood. And so we will start off with the basics first. So first off, we would introduce an important tautology. Again, remember what a tautology is. We have covered tautologies here. So tautologies are statements that are always true regardless of the truth or falsity of the statement, that is. So we have tautologies like schizomizo, modus penus, etc. And in here, we're going to show you a very important tautology that looks kind of complicated, which is this: reductio ad absurdum. What this means is actually that if not P implies C, and if not P also implies not C, then that means that not P is never going to be true. And so it's going to imply P. What this basically means is that if you say something that implies some other thing is true and false at the same time, then you have reached a contradiction, and you have contradicted with the law of the excluded middle. And as such, the original statement must be false. This is the essence of the proof by contradiction, and this works for everything. If you're trying to prove a general statement P, what you need to find is some C that you can contradict on. And this is what we mean by proof by contradiction. It means using this tautology to prove P. And in some sense, you can also think of this as like a final step in a direct proof. When you're doing direct proof, usually we do something like this, and then we end up with B, and then we end up with B. Instead of doing that, we would use this as the second last step, and we would try to prove this instead of proving P. So how do we use proof of contradiction for a implication statement? Well, we could do that if we replace P with A implies B. So if we replace P with A implies B, then we can use this strategy to prove A implies B. So, well, how do we do that, right? So if we want to do that, then we need to figure out what not P is, right? And as an exercise, you can try to prove that not P is equal to A and not B. And so by reduction ad absurdum, we get this very complicated tautology. So what this means, if we try to unpack this, is that if we want to prove A implies B, what we can do is that we can first prove that A and not B implies some C, and then we can prove that A and not B implies some not C, and then if we combine those two statements together, then we can prove A implies B. This is what we mean by whenever we're doing a proof by contradiction. And so I hope that you can see that a proof by contradiction is actually something very specific. It's not something that you can use all the time, and it has to be in this format. And so whenever you're writing something down as proof by contradiction, make sure that you're actually using this tautology. Make sure that you have a good P, you have a good C, and make sure that it's written as clearly as possible. So now we're going to use some examples, right? So how do we prove, for example, how do we prove that x is even implies x squared is divisible by 4? So A is going to be x is even, not B is going to be x squared is not divisible by 4, and we also want to find a C and a not C, so that we can prove this and this, right? So in the proof 1, we're going to instead of finding any interesting C, we're going to let C be B. So we are going to let C to be x squared is divisible by 4. And in here, we can do, okay, well, x is even and x squared is not divisible by 4. Well, we can kind of ignore this and statement, right? We can just copy our direct proof and then turn this x is even into x squared is divisible by 4. And then this would kind of be attached to the end of it all the way. And we would end up with x squared is divisible by 4 and x squared is not divisible by 4. And so now we have C and we have not C. And so we have proved this statement and we proved this statement at the same time. And so by reduction ad absurdum, we have A implies B. And then in proof 2, we can do a very similar thing. And this time we're going to let C to be A. And then we end up with C and not C. And so by reduction ad absurdum, we have A implies B. So you can see that, proof 1 and 2 are actually just direct proofs in disguise, right? We didn't actually find an interesting C. We just did a direct proof. Now, you may think that this is very stupid, like why would anyone do this? But as it turns out, in mathematics, you actually do end up with these situations a lot of the time. If you're not careful when you're doing a proof by contradiction, you may realize that you may think that you're doing a proof by contradiction, but what it turns out is that you're actually just doing a direct proof. And in that case, it is much, much better for the reader if you have simply packaged the entire proof as a direct proof. It makes the thing much easier to understand. And so this is a very important tip, which is that whenever you're doing a proof by contradiction, make sure that the C you're choosing is a non-trivial one. If it is just B or if it is just A, then please rewrite the proof and repackage it as a direct proof. You can see, like as I've said before, always check if your proof by contradiction can be simplified into a direct proof. So if you want to find a true proof by contradiction, you can check out the proof of irrationality of square root of 2. I'm sure a lot of you have read that before. It is a true proof by contradiction because it shows a non-trivial thing to contradict all. And as for how you would prove a if and only if statement, you would basically do two things. You would prove if A then B, and then you would prove if B then A, and then you would prove, as a result of that, A if and only if B. That is very simple, I think. So summary. So if A then B, and if not B then they're not A, are equivalent statements. Remember this. Contrapositives. It's a very, very, very important thing for you to remember, and it could save you a lot in various situations. Also, how do you prove if A then B by contradiction? First of all, you assume A and not B, and then you find a C such that A and not B implies both C and not C is true. Make sure that C is not A or B, and that would be a great proof of contradiction. So yeah, that's basically the end of the lecture. So for the further reading, I would recommend you to read the TMUA notes in full yourself. If you have the time and the interest in this topic, please read Introduction to Mathematical Logic. It is quite a tough book to read. It is quite terse. The link is in the Google Classroom, but I really would recommend you to try reading a mathematics textbook on your own. Trust me, it will seem very difficult. Reading 9 pages would take you like 2 hours or 3 hours, but that's absolutely fine. That is basically what studying mathematics at the university is like. And if you can get yourself accustomed to reading terse mathematics early on, it is going to be very helpful for you to understand whether you actually like mathematics at the university level and whether you are genuinely interested in studying mathematics at the university. So please read the book. And again, this lecture is very short. It's very hard to cover all the material. So please read the book. Please try to watch this video again. Please try to find more resources on your own to try to get a further grasp on this topic. Again, be curious, learn on your own. That's very important. So for the problem sheet, please do the problem sheet. I think there's some really exciting problems in the problem sheet. So please do it, and please hand it by the deadline. I probably wouldn't mark it if you hand it in late. In the problem sheet, there's also a tutorial schedule, which is an Excel file. Please fill that in so that you would have a tutorial scheduled. A tutorial is basically like a 1 to 3 to 4 students, kind of a short lesson, a short class. I would be able to kind of cover the mistakes that you've done in your problem sheet. You can ask me questions about Oxford, about the lecture itself, and we might even be able to talk about some extra problems or something like that. So it's a very exciting thing. Please make sure that you fill in the forms by the deadlines. Also, the next lecture is at 20th August. I'm sure Angus would notify you of the timing and schedule and all of that. And yeah, so that's basically it. So do you guys have any questions? I'm going to hang around for maybe a few minutes, and yeah, that's great. Thanks for listening. Great.